Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, I'm going to go over finding the arc length of any curve, arc length. Okay, so when we say arc length, really, we are going to get some part of a graph. I'm going to enlarge it a little bit and say I'm going to take a very small segment of it, let's call it ds, and try to find how we get this ds if we know the function. So we know that function of x is given to us, okay? And so I'm going to do is I'm going to take a very small piece, ds, and that would be a straight line, right? When you take it very small, you can consider it as a straight line, and then you can form a right triangle, a right uh, Pythagorean triangle, in which case the base would be dx, the height would be dy, and the equation relating them, as you all know, is dx squared plus dy squared equals ds squared. Meaning, if I want to get ds, I will take the square root of dx squared plus dy squared. Now, the trick we play so that we can find the length of the arc is to multiply, say, outside, if we have the function as f of x, is to multiply by dx and divide by dx. You all know that if I take dx and let it go inside the square root, it will go in the denominator as dx squared. So now you will get the square root of dx squared over dx squared plus dy squared over dx squared dx. Of course, the first term is 1, so you get the square root of 1. dy dx, we can call it y prime, but it's squared, right? Because I divided by dx squared, so plus y prime square dx. And y prime square is f prime, so y prime is basically f prime of x. So I can use this equation to solve the problem by integrating, of course. So if I integrate the left-hand side, I get s, which is the total length of the graph, and that would be the integral. Let's say I'm going from point A to point B. So from A to B of the square root of 1 plus f prime of x squared dx. If the function is given to me as h of y, for example, so it's a function of y, it would be 1 plus f prime of y quantity square dy. Another thing we can do is parametrization. So we can use a parametric equation like I went over that in a session before. And now at this stage, instead of multiplying dx by dx, you would multiply dt by dt. And from here, you can get ds equals the square root of dx dt square plus dy dt square and dt outside. So let's take a couple of examples that will show us whether we have an easy function that we are given, like f of x. And of course, f of y would be similar. There is no reason to take another example similar to that. But let's come up with an example. So here we say, suppose I want to have the length of a function f of x that equals, let's say, most of these problems, by the way, will involve integrals that are hard to integrate. So we take an easy example, but in the worst case scenario, once you come up with the equation or with the integral and you see that it's really hard to do, you can use a computer to find the length. So it's not really a big deal. 6x to the 3 halves. And let's say x goes from, what can we do that? Let's take an easy one. So let's say greater than 0, less than 2, something like that. So according to this equation, I can write ds. First of all, in order to, what I need is f prime of x, right? Because I'm going to say it's the integral, or at least this is the square root of 1 plus y prime square. F prime of x is really going to bring down the power. 3 halves times 6 is 9. And then you reduce the power by 1. So you get 9 root x. Meaning f prime of x quantity square would be 81x. So now my ds would be the square root of 81x dx. Meaning the length of my graph would be the integral from 0 to 2. Of course, the 81, I'm sorry, 1 plus 81x, right? 1 plus 81x. Um, the square root of 1 plus 81x dx. You can use a very easy substitution. In fact, you don't even need a substitution, but let's say let u equals 1 plus 81x. So du becomes 81 dx. I don't have 81 out, so I can say dx equals du divided by 81. So that would be 1 over 81, the integral of the square root of u, and then dx divided by that. Dx is du over 81. Okay, so this is u to the 1/2. When I integrate it, I will get u to the 3 halves over 3 halves, or times 2/3. And then, as I said, you have two ways to do it. Either you change the limits of integration, and you can do that easily, or you return back the u, replace it with 1 plus 81x. So it's really up to you. So we can say this equals, notice this would be 2 over 243. And then instead of u, I'm going to say 1 plus 81x evaluated from 0 to 2. So it's 2 over 243 times. When you substitute 2, you get 162 plus 1. I'm sorry, it's over to the 3 halves, right? Why didn't I write that? Okay, so when you substitute 2, you get 162 or 163 to the 3 halves minus, and when you substitute 0, you get 1 to the 3 halves. And then you can use a calculator to evaluate that, and that will give you 2 divided by 243, and then between parentheses 163 raised to the power of 1.5 minus 1. And that equals 17.12 units of length. Okay, so again, what we did is first we found f prime by taking the derivative of 6x to the 3 halves, which is 18 over 2 or 9x to the 1/2. You square it, you get 81x. You add 1 to that, because that's the square already. You add 1 to that, you get 1 plus 81x. And again, you just substitute this value with u. So du becomes 81 dx, or dx here, I substitute it with du over 81. And the integral of u to the 1/2 is u to the 3/2 divided by 3/2. 3 times 81 is 243. And now this whole thing is raised to the power of 3/2. When you substitute 2 times 81 is 162. So you get 162 to the 3/2 minus, when you substitute 0, you get 1 plus 0 to the 3/2 is still 1. And the rest is history. Now let's take another example, but this time it would be a parametric example because that would help us in the next video where we will introduce line integrals. And in line integrals, the easiest way or the most common method is to just use a parametric equation. So in this example, let me see, I think I had come up, or I found an example, I made some changes to it. Oh, suppose here you have a function, a parametric function, x of t is, and y of t is. So here we say some linear function. So like let's make it something easy. So 4t maybe plus 5, and maybe this is 10 minus 3t, and t goes from 0 to 1. And you want to find the arc length when t changes from 0 to 1. Okay, so again, you can come up with, you do backwards and you can come up with a value of t and then substitute and get the relationship between x and y, but it's much easier to do it this way, right? Because first of all, we need to find dx dt. It's simply 4, and dy dt, and it's simply -3. So now we say the arc length equals the integral from 0 to 1 of the square root of dx dt square plus dy dt square dt. That's a very simple problem. I just use the numbers 4 and 3 so that we know that that's in using Pythagoras, we get 5, right? So this is the integral from 0 to 1 of the square root of 16 plus 9, or 25 dt, equals, this is square root of 25, or 5. 5 is a constant, so you get 5. The integral from 0 to 1 dt equals 5t evaluated from 0 to 1 equals 5 minus 0, or simply 5. Very straightforward. Again, the idea wasn't to find how, or to teach you how to find integrals, right? We covered that in many sessions before. It's simply I wanted to show you how to find the arc length if you have a parametric equation or you have a function of x or even a function of y. Should be very straightforward. Wait for me in the next session. We are going to go over line integrals and see how parametrization would make it very much easy for us to solve. Thanks for your time. Hope to see you soon.